Yes, I will. And we'll start from the current slide. But before we start with the trig, I have a couple of announcements. And one of these is sort of general, but it's pretty short time fuse for you guys, okay? And here's what it is. Lawson State Community College Transfer Fair Days 2018 was yesterday and today. Yesterday it was on the Birmingham campus. Today it's on this campus. Unfortunately, they're starting right now, okay? But the good news is they'll go until 11:30. So when you get out of here at 10:45, you still have 45 minutes. You can catch the folks down there, okay? So this goes to 11:30. And they say here in the Bessemer Faculty Campus Cafeteria, which I've never heard it called that before. It's called the Faculty Staff Dining Room. That's what it's labeled as and stuff like this. I don't know if you know where it is. If you don't, let me point it out to you. Okay? If you go out of this door here and into the hallway here, just make this quick zig there. Go down this long hallway this way. Don't go to the end. Go to the second stairwell, not the first one, but the second stairwell. Don't go all the way to the end. Come back to that stairwell. Go down half a flight, and then you're on this part of the first floor. And you have to zig around here too. But if you take, you go straight through the doors at the bottom, and then take a slight right, and then a left again, and it's up here on the left. It's the faculty staff dining room. There's an entry off this hallway, an entry off that place where you turn into to go to the cafeteria. You can go into the cafeteria, and there's an entrance this way as well. So there's 3 different doors that you can go in. They are set up there. They're setting up right now. They will be there for the next 2 hours. We'll only be here an hour and 15 minutes, so you've got plenty of time to get there after class. And not just that, listen to the schools that are supposed to be here. I don't know how they're going to fit them all in the same room, but I guess they will. AUM, Mississippi State, Oakland University, University of Alabama, and they have some smaller divisions here too, Montevallo, Alabama State, Auburn University School of Forestry and Wildlife Sciences, and Auburn University, so they'll have 2 tables there, Alabama A&M, University of West Georgia, Jacksonville State, Stillman College, UAB, UAH, University of West Alabama, Troy University, University of South Alabama, and another Alabama College of Continuing Studies, that's University of Alabama, Athens State University, UAB School of Health Professions, University of North Alabama, Samford, Fisk University, Mississippi College, Concordia College in Alabama, I don't know exactly where that is, but I'm sure it's here somewhere, Tennessee State University, William Carey University. Now this one I'd never heard of, Aveda Institute in Birmingham. And one of my students in the last class said they do cosmetology there. Okay. Armstrong State University, Faulkner University, Southeastern Bible College, Talladega College, Georgia Southwestern State University, and Berea College. Okay. So lots and lots of schools there. Hopefully they're all there today. None of them went home after yesterday, but they are there until 11:30.
You said they're here for something transfer thing?
Second?
You said they're here for a transfer thing?
Yeah, it's transfer day. What it is, they have the information and the procedures you need to go through to transfer from Lawson to go to their school. They sometimes have transfer scholarships. They have, applications. I mean, they can answer your questions about if you want to transfer to any of those schools, they're there to answer your questions. Yeah. Okay? Now, here's another one. This one's specific to this class. That's why I want to make sure I was recording this so people would hear it. This is from Miss Nyla Gerasi. Y'all know her from the Birmingham campus? Okay. She is our math team coach. Now, I've worked with the math team the last 2 years. We just started it 2 years ago. The first year, we got it started in the fall and started having practices and stuff and went to the first competition. They came in 4th, just from scratch. I mean, it was really pretty good. Then last year, we tried to do the same thing. We just waited till fall and tried to get a team together and get practices done. We didn't have, it was harder to work out schedules and stuff. They went and they didn't do as well as fourth. Okay. So this year, Mr. Race, and this is what the teams that are very successful do, they have it all year round. Okay. So she's starting to have the practices and things like this starting tomorrow. Okay. Every Friday at noon on the Birmingham West Campus, the C building, that's the science building, and C100. Okay. Now, what she's asking for, she's asking us, the instructors, I'm trying to build a strong math team. Please, if you have a student in Math 100, 112, 113, or 125, or even higher in calculus if you wanted to, who will be at Lawson State in the fall of 2018. Will you still be here? Oh, good. You still be here? Excellent. Both of you are candidates, okay? If you want to participate, it is fun, okay? And you actually learn math really well, and it's fun doing it. She'll have practices over there at Friday noons. If you prefer this campus, I'll hold the practice anytime during my office hours. And you can go back to the website, the Blackboard, and check out my locator card. And, yeah, anytime, just come see me. If we can get a group, that's better, even with one person. I'll do practices anytime you want to. We have some of the old questions they've asked before. We'll go through those, get you used to those kinds of questions. Okay? Now, if you want to contact Ms. Gerasi, I have her email address here. I have her office number. And she is located also in the science building, but she's up on the second floor. Her office is in 210. The practice will be down in 100. Okay. So please consider it. Consider it seriously. It's a lot of fun, and you'll really learn math well and have a great time doing it. All right. Any questions or anything we've done so far? Okay. We left off last time in section 4.2. Chapter 4 is trigonometry. 4.2 is trigonometric functions on the unit circle. And we just talked about what those 6 trigonometric functions are and how they relate to the unit circle. In those definitions of the trigonometric functions, note that the tangent and secant cannot be defined when x equals 0, because what they are is 1 over x. And of course, x can't be 0. Well, where is when x equals 0? Yeah, when x equals 0, that's up here at pi halves and down here at 3 halves pi, and any 2 pi multiple of those. Okay? For instance, because t equals pi halves corresponds to the point, x is 0, y is 1. That's up here. Pi halves, you're up there. 0, 1, x can't be 0, so the tangent function is not defined at pi halves. Okay, it follows the tangent of pi halves and secant of pi halves undefined. Okay, and we'll see how those graphs look the second half of this chapter. Okay, similarly, the cotangent and cosecant functions are not defined when y is equal to 0. Where is that going to be? It's going to be at 0 and pi and any multiple of pi. Okay, positive or negative multiply of pi. Because t equals 0, you're at the point 1, 0. Your y value there is 0. You can't have that. So cotangent 0, cosecant 0, and pi and any multiple of pi, positive or negative, are undefined. And we'll see how that looks on a graph later. So keep that concept in mind. Okay, any questions? Now, in this figure, and this is not a bad figure to have. Actually, there's a better one, so I'll just hold off on this. The unit circle is divided into 8 equal arcs. Okay? See what they've done here. Here's the unit circle. And coming in alphabetically, this is Sarah. Okay. unit circle, 8 equal parts. That means divide it in half. You got 2 equal parts, quarters, 4 equal parts, and then divide the quarters into equal parts, and you got eighths. Okay? So, if you think about this, this would be going around the unit circle here, 2 pi all the way around. Halfway around would be pi halves. Half of that would be pi. Half of that would be pi halves, and half of that would be pi quarters. So here are the divisions. The t is equal to 0, pi quarters, pi halves, 3/4 pi, pi, 5/4 pi, 3 halves pi, 7/4 pi, and 2 pi. Okay? Those are those divisions. Now you can go the other way around, having them negative. You can go round and round and round and round, just add 2 pi to them as many times as you go around. Or subtract 2 pi if you're going in the opposite direction. So those are the values for the t's, the t value, the arc lengths of each of those points. Now, they also give the xy coordinates there, and they just sort of pulled these out of space somewhere, okay? Why in the world would that be square root of 2 over 2 for x or y at this point right here? Well, there's a pretty reasonable reason for that, okay? First, think of this as dividing that quadrant exactly in 2. That's the line y is equal to x, isn't it? Is that line? The y value is the same as the x value, okay? Y here is the same as x there because it has to split that quadrant exactly in 2. So it's a diagonal line. So y is equal to x, okay? Now, what kind of circle was this? The unit circle, which means what? Second?
It's 1 unit in radius.
Okay, yes, the radius is 1. So what would be the equation for that circle? Do you remember that? Let me get my pen set up. What's the equation for that circle? X squared plus y squared is equal to 1 squared, or 1, right? Now, I made you say it. I twisted you around till you had to say it, that x is equal to y, right? On that line, on this line right here, x is equal to y. Also down here, they're both negative down here. It's x equal to y. Well, if x is equal to y, then I could write this as x squared plus, instead of y squared, make it x squared, because x is equal to y is equal to x, right? Is equal to 1, right? Now let's solve for x. What could you do first? 2x squared. 2x squared is equal to 1. Now what? Divide by 2, if I could write. And that gives you x squared is equal to 1/2. And then what would we do? Square root of both sides. So x equal to, now I'm going to leave off the plus or minus now, but it really should be a plus or minus. It would be the square root of 1 over 2. Which, because I know what the square root of 1 is, that's 1 over the square root of 2. Right? Now, many times in math, especially back in the old days, when I was growing up, okay, you never liked having radicals in the denominator. Do you know why that was true? Because back then you had to figure out things by hand. This is before calculators, believe it or not. I saw my first calculator, my very first calculator, my sophomore year of college. Okay? I'm that old. Okay. Believe it. Okay? I was at Georgia Tech, and first quarter sophomore year, I was taking my first college physics class, engineering physics class. Big lecture room, probably held 200 students in there. And 8 o'clock in the morning, I had Dr. Ewald, I think his name was. Okay, and we were all got to class and were sitting in there. We had heard about these things, but I had never seen one before. and in walked two guys with this thing strapped to their belt. That's how they used to wear them, believe me. Strapped to their belt. In walked that. Now the rest of us had, y'all probably never even seen one, slide rules. Okay, you've seen one? Yeah. Slide rules. Slide rule isn't exact, but it gives you approximate answers. Usually you can get maybe 3 digits, and that's about all. Basically what you're doing when you're multiplying or dividing big numbers, you use scientific notation and you add or subtract logarithms, because that's the same as multiplying and dividing numbers. We'll get to that. Well, did y'all get to that in the last course in 112? Logarithms, okay. Well, that's what, huh? Yeah, okay. And that's where you use them in slide rules, okay? No one, well, people do use them now, but not that way anymore. So, in walk these two guys, nerds we called them, okay? In with these on their belt, and the rest of us let out a sigh of, oh no, there goes the curve. Because those guys could get exact answers. And let me tell you about those big old boxing looking boxes they were wearing on their belt. Number one, they had to sit near a plug because they didn't have as good of batteries as we do now. And number two, they could add, subtract, multiply, and divide. And that's all at the time, okay? Within months they could do bigger things and better things, but so far that's all they could do. And they cost about $600. Yes, okay? This is brand new. That's why I didn't have one. I had a slide rule. I think I had gotten it from my dad, or else I had bought one in the bookstore. But they were not $600, okay? So, that's the first calculator I ever saw. They were HPs, and then within a short time, TI, Texas Instruments, came out with some competitive. And once the competition got there, the prices started going down. And they got better and got more functions, and then a few years later had the battery ones that you didn't have to have plugged in all the time. So things got a lot better. But back before they had the hose, if you were doing this, if someone has a calculator now, it would be helpful. Can you plug in what the square root of 2 is? Back in the day when, to calculate what value that would be 1 over 1.414. There's the first 4 digits, but give me a few more. Square root of 2.
1.4142135562.
Okay. Now, if I wanted to get a pretty good approximation of that, I would then take this number, divide it into 1.00000000000, as many zeros as you want, and then I'd have to move this decimal. Do y'all remember how to divide by decimals? You probably don't, because you used a calculator, didn't you? Okay, so you would move this. Yeah, you move it 1, 2, 3, 4, 5, 6, 7, 8, 9 places. You'd move this one 1, 2, 3, 4, 5, 6, 7, 8, 9 places. Put the decimal up here, and then start dividing that big number into that one by hand, no calculators, and that's how you did your division. A big boo hiss, okay? All right, now, so mathematicians, I don't know if I've told you this, probably told Daniel this, but y'all weren't in my class last time. I have this theory about being good at math. I think to be good at math, you have to be a little bit lazy. Do any of you qualify? No, you're all, oh no, okay, we have some, but now if you work hard, you can still do well in math, okay? But if you're a little lazy, you're probably going to do a little bit better, because mathematicians are always trying to find out the easiest way to do a problem. And here's what they found out. What if we take this here and multiply numerator and denominator by root 2? What's root 2 over root 2? 1. When can you multiply by 1? Anytime you want to. It doesn't change the value at all, right? Okay. So this becomes then root 2 over, and what is square root of 2 times square root of 2? 2. Now guess what? I can do square root of 2 over 2, bring down the root 2. Root 2 is 1.414213562. And I can do that math with my decimal here, and that's going to be a 707106781. I can do that math in my head. That one I cannot. I would be taking pages of things to do that division, whereas this is the same division, and if you did that, you're going to get the same number. So you see, mathematicians need to be a little lazy, find out the easiest way to do it. Now this process here is called rationalizing the denominator. You don't want an irrational number in the denominator because it has all these digits that never repeat. Okay? But if you have a rational number down there, it's easy to divide. Okay? So that's what got you into the habit of rationalizing denominators. And then when you got this, that's where they came over root 2. That's what the x value is. And then we know x equals y, so the y value is that too. Okay? Then up here we know this is 1, 0, that's 0, 1. Over here, it would be minus root 2 over 2. Let me erase some of that out of the way because that's just there in the way now. Okay? Now you're minus root 2 over 2 here, and positive root 2 over 2 here. Down here you're minus root 2 over 2 and minus root 2 over 2. Over here, positive root 2 over 2 and negative root 2 over 2. So there you have all of your ordered pairs. And guess what you can do with that? When t is equal to pi fourths, what's the sign? Well, this is pulling back from yesterday, from Tuesday. Oh, that was 2 days ago, long time. What's the sign of a pi fourths? The y value. What's the cosine of the pi fourths? The x value. What's the tangent of pi fourths? The ratio of y over x, which is 1, because they're equal to each other. And then the cotangent would be x over y. Again, 1. Secant would be x over 1. It's the reciprocal of the cosine. Right? Yeah, okay. And cosecant would be reciprocal of the sine. Oh, yeah, reciprocal of sine. So, okay, let's get those then. Because they're reciprocals, that's 1 over this thing. Okay? So that puts your radical back in the denominator. So let's go back and make that 1 over root 2 and just flip that. That gives you root 2. Flip the other one to get root 2. So you know the sine, the cosine, you know all 6 trig functions if you know those ordered pairs. You know them for here, 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 here. Now the only thing, remember, up here you don't know tangent and secant because it's not defined. Over here you don't know cotangent, cosecant. They're not defined. Or here, tangent and secant not defined here. But all the rest of them you know. If you know the ordered pairs, you know what the values are. Right? So here from this simple little thing, we now know without a doubt, anytime you have t equal any of those values there, you can give me the any one of the 6 trig functions. You may have to sit and think and write a little bit, but piece of cake, almost. Marble cake, it may be a little hard, but no, I'm sorry. Okay, never mind. Okay. Now, what if we divided that unit circle into 12 equal pieces? In other words, take the unit circle, divide it in half. That would be pi. Divide that in half, and you get pi halves. But now, rather than dividing that in half, divide it into thirds. Okay? So that means this is 1/3 pi, 2/3 pi, pi. And half of that would be 1/6 pi, 1/3 pi, pi halves, 2/3 pi, 5/6 pi's, pi, 7/6 pi, 4/3 pi, 3/2 pi, 5/3 pi, 11/6 pi. Okay. They're just fractions. Okay. Now, out of the blue, or somewhere in the Never Never Land, they've come up with fractions to put there for the ordered pairs. Where did they get those? Well, we're going to do something, not the same as what we did before, but we're going to do the same type of, well, we're going to do a process that will get us there. So what I'm going to do is take two of these slices. Picture that as a pizza, I think, in terms of food. You know, and you slice it 12 equal pieces, okay? And two of those is going to be a sixth of the pizza, right? Now, I'm going to choose those two. Now, what circle is this? Unit circle. That means it's a radius of 1, right? And this is the radius of 1. Now, all these radii are 1, right? It's a unit circle. Okay. So this is a 1, and that's a 1. And what did we say the angle is here? You can give it to me in radians if you want to. We just said that. Each of these would be a sixth of a pi, so two of those would be a third of a pi. Pi-thirds. Now, if we go back and change that to degrees, here's the easier way to do that. Take 360 degrees and do 1/6 of that. What would that be? 60. Yeah, with a lot of confidence there. She said, okay, yeah. All right. So 60 degrees. Now, if that angle is 60, this is a little bit of geometry here. I'm going to do something else here. I think I'll do it in red, just because that's in red. Okay. I'm going to, did it take? No, it didn't. What won't it take? There, we got it. Okay. I'm going to do a little dotted line and connect those two. Okay. Now, I've got a question for you. Do you buy the fact that is indeed a perpendicular line to the x-axis? In other words, it's parallel there. These 2 points are directly one over one another. Do you buy that? Okay? Okay. Okay, agreed on that. Now, and this is, and if this total angle is 60, that's 30 and that's 30, right? So that's exactly cutting back into, right? Now, would you also buy the fact that these two angles must be the same? Parallel, that these two angles must be the same, right? Okay. If this one's 60 and these two are the same, you want to give them a name? Make up a name for them. Second?
Like ABC?
Yeah, that'll be fine. Wait, no, just A. Okay. Yeah, it's the same. Okay. Let's call this angle A. And we know this is 60 degrees, right? And this has to be A also because they're the same, right? So this gives, and what are the three angles of a triangle always add to? Second? 180, 180. So you got 2A plus 60, right, is equal to 180. Buy that? Okay. Subtract 60 from both sides. And you get 2A is equal to 120, right? I should have degrees there. I don't with this. Okay. Divide by 2. And guess what? A is equal to 60. That's what we call an equilateral triangle. Equal lengths, lateral length. All three sides are equal, and all three angles are equal. Are you buying all this so far? You don't think I've snuck something in them? Okay, this is absolutely correct. Okay, so if all three angles are equal, that means all three sides are equal. So this has a length of 1 also, doesn't it? And if that's exactly cut by this, what would be this height here? Hey.
It's one of the 977 birthday.
Yes, I announced it already today. I told them they have 45 minutes after class. They can get that. Okay, thank you so much. All right. Yes, look at that. Okay, so this is 1/2. So this length here is 1/2, and what's that value? Is that? It's the y value. So therefore, the y value is 1/2. Oh, we just saw that, and this one's negative 1/2. Look at that. Okay, now we know that this is also a right triangle here, didn't we? Didn't we agree to that? And what can you tell me about a right triangle? Does some theorem come to mind? Ah, excellent. Okay, a squared plus b squared is equal to c squared. I heard her say, right? Now, what would be our a and our b? Oh, we've already used a and b. Let's forget these a's, okay? We're off to a new problem here, so we're not going to call those a's anymore. Okay, now we're going to call something else A, B, and C. In that little triangle right there, this is what you want to call A. In fact, okay, you tell me, is it going to be horizontal or vertical or this angle? The horizontal, okay? And what do we usually call the length on the horizontal axis? X. So let's actually call that x, okay? So this will be our value x, that will be our value y, and we already know what it is, huh? 1/2, okay? So what we have, and if the horizontal is this, whoops, let me get my pen back. So this would be x squared plus 1/2 squared, that was your b, right? And what was your c? I forgot. Did y'all tell me? Well, tell me. 1. 1 squared is 1. Perfect. Okay? So, this will be x squared plus what's 1/2 squared? 1/4. Perfect. Is equal to 1. Okay, so the next thing we're going to do is, let me erase some of this other mess here. We already established all that. So we don't want that anymore on my screen, messing it up, okay? So what we would do next? Subtract 1/4 from both sides. Okay, that'd be x squared, this goes to 0, is equal to, and what's 1 minus 1/4? 3/4, okay. All right, now what do we have to do? Take a square root. Okay, so x would be equal to, I'm just going to do the positive now. You could do positive and negative. We'll see those are going to pop up later. What would that be? The square root of 3 over the square root of 4. What's the square root of 4? 2. And what's the value of this? Oh my goodness, x is equal to the square root of 3 over 2. What's that?
That makes so much more sense now.
Yeah. They didn't just pop them out of the air. They really have those values. Okay? Now, if that wasn't enough, if you rotated this one up here, okay, now, I don't know if you would buy this or not, hopefully you would, that this is now your y value would be corresponding to what the x was here because we just rotated. See, this was 30, 90, that would have to be 60. Rotate it up here, this would be 60. That would be your 30, and this would be your 90. So therefore, this would be, the x would be what the y was here, 1/2, and this would be 30. See it? Okay. And then this up here would be 0, 1. I mean, that's what it always is. And this one over here is going to be exactly the opposite of x, minus 1/2, but the same y, root 3 over 2. This will be the opposite of x, minus root 3 over 2, but still the same y, 1/2, and this will be negative 1, 0. This one down here is going to be the same x as this, negative root 3 over 2, but the opposite y, negative 1/2. This will be the same x, negative 1/2. opposite y, negative root 3 over 2, 0, negative 1 down here. This is the same x here, 1/2, but the opposite y, negative root 3 over 2, and this one's the same x as this, root 3 over 2, with the opposite y, negative 1/2. So there we have ordered pairs for every one of those 30-degree. Okay, let's get back to radians. Pi 6, pi thirds, pi halves. We did that before, didn't we? So that's what we have. Oh my goodness, here we have a whole bunch of other ordered pairs. If we know the ordered pairs, guess what we know? All 6 trig functions. Right? Because your sine is always the y value, the cosine is the x value, whichever one you're at. Okay? The tangent is y over x. The cotangent is x over y. The secant is 1 over x, and the cosecant is 1 over y. Which, in that case, that would be 2. That would be real easy to do. Okay. And on those root 3s, when you move them to the denominator, you have to rationalize. You don't have to. Nowadays that we have calculators and computers and stuff, you don't need to do that anymore. But to begin with, the book will always do it, and then later on they'll get around to not doing it. Get used to seeing them both ways. All right, does that make sense? All right. So you know. Refresh your mind, get used to them, get to know them. I mean, I really don't care for memorization. If you're a good memorizer, I mean, use it. I mean, if you got that skill, use it. But I'm not a good memorizer, so I always have to have a pattern or think through issues and stuff like that, because I never can remember things well. As you notice, I get your name wrong always. No, okay. Okay, but the where was I going to that? I was going to say this. Did you ever sit down and memorize your name? Probably not. You just got called that so much, you knew it was you, and you use this one. Same with Social Security now. Maybe at one point I memorized it, but now I just write it down so much that I know what it is. So, or whatever, ticket number, whatever. Once you use them enough, they become family. Okay, friend, you know what they are. Get to know them. Okay, both of these. Get this, use them enough, and soon you hardly even have to think about them anymore. Okay. Now they're going to tell you how they got them, and we've already been through this. To verify the points on the unit circle in the first figure, that root 2 over 2, root 2 over 2 also lies on the line where y is equal to x. That's exactly what we did, and they went through the same steps. But why didn't they do that first rather than later? And they, when they took the square root, actually did plus or minus. The plus comes here, the minus is over there. So either one of them. So that's where those came from. And the points in the first quadrant are plus, 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 minus, plus, minus, minus, plus, minus. Okay. You remember that from the graphic. Okay. So they're all root 2's over 2 for those pi quarters, the quarter pi things. So just assign the right sign to them, and you got them. Now, when I say sign, I usually have to spell it S-I-G-N sign as opposed to S-I-N sign. There's so many signs going around. Okay. Now, this one, they said you can use similar reasoning, but they don't tell you what it is. I told you what it was to get those, but that's those that we had before. Okay. Now, here's example 1. We're going to evaluate the 6 trigonometric functions at each of those real values. So let me get back to my black here, or dark. It's not really black, but close to it. So what we want to do is the sine of pi 6, the cosine of pi 6, the tangent of pi 6, the cotangent of pi 6, the secant of pi 6, and the cosecant of pi 6. All right. Now, do you remember what the order pair was that corresponded to pi 6, t equal pi 6? Okay. We'll do a visual here. Pi 6 is a little piece right here, and its coordinates were root 3 over 2, 1 half. Now, let's do it. I'm going to interpose this circle on that circle, okay? All right. And let me go back to my red again. Here we go. There's the pi quarters. There's the other. There's that one. There's that one. They're not pretty, very pretty. And let's put the values on. This one was root 2 over 2, root 2 over 2, and so on. Okay, I'll just stick in the first quadrant. Okay. Now, and these are the ones. Pi 6, pi quarter, pi thirds, pi halves. Starting at 0, pi 6, pi quarter, pi thirds, and pi halves. Okay? Now, this is a little trick here. Let's look at the y values of those. 0, 1 half, root 2 over 3, root 2 over 2, root 3 over 2, and 1. I'm going to write those slightly different. Okay? I'm going to write 0 as the square root of 0 over 2. That's still 0, right? This is the square root of 1 over 2. That's 1, right? This is the square root of 2 over 2. This is the square root of 3 over 2. This was the square root of 4 over 2, the y value. What's the square root of 4? 2 over 2 is 1, and sure enough, that's your y value there, isn't it? So this is the easy way to remember the y values. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4. You just have to remember what angle that represents. Now, how about the x's? Start up here. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. Just goes the other way. So, now I don't have to memorize because I've got a pattern. I hate memorizing, so I love patterns. Okay? I just have to remember that stands for these. Our favorite angles, pi 6, pi fourths, pi thirds, pi halves. 0 to start with. Okay? So let's go back here, pi 6. Okay, I know that's a lot to remember the first time. So what was your sign is the y value. What was that first y value? One over 2. Okay? Now, if it helps, write down the ordered pairs. Just write down the whole thing. As soon as I give you this, write down. That's root 3 over 2, 1. 1 half, sorry. Write it down, okay? If that's helpful, then it makes the rest of this pretty easy. What's cosine of pi 6? Sine of pi 6 is the y value. Cosine of pi 6 is the x value. So that would be root 3 over 2. And the tangent is, now, here's the reason I write them this way. Okay? Because tangent is sine over cosine. Y over x. So do this, the 2's go out, and you have 1 over root 3. Just a piece of cake, right? Except that's irrational, so you could write that as root 3 over 3. And that's how the book likes to write it. Now, later they'll change it. You multiply the numerator and denominator by root 3. Okay? Got it? So that's fairly easy to do. Now, cotangent. Cotangent is reciprocal of tangent. It's x over y. So basically take this thing here and reciprocate it. Root 3. Root 3 over 1, right? Secant, and that's why I wrote it next to it, is the reciprocal of cosine. So that would be 2 over root 3. But if you don't like having the radical in the denominator, multiply numerator and denominator by root 3, because root 3 over root 3 is 1, and you can multiply by 1 anytime you want to. So this will be 2 root 3 over 3. You don't have to do that, but you can. And then this one's really easy. Cosecant is reciprocal of sine, so that's just 2 over 1. 2. So really the only thing you have to remember, find the angle, find where you are, Waldo, okay? Then get your ordered pairs. Once you have your ordered pair, y goes here, x goes here, the ratio of those go here, reciprocal of that ratio goes here, reciprocal of that goes here, reciprocal of that. All you need is none of these two, and then the rest of them you can calculate. I don't like to memorize, so if I can find a little pattern like this, I'm happy camper. Okay? So, can I go and erase this? Have you got it? I'll let you get it if you want to get it. Everybody got it? All right, so okay. Take your time. To me, trig is just so neat because it always follows the same rules, you know? And the rules tie together so well. And that's what makes me think of Math 113 is so much easier than 112. Maybe other people, if you're used to algebra and not used to trig, oh, you like the algebra part. But boy, trig just, to me, makes so much sense. Okay, everybody got it? Let's move to the B part. I'll erase all that. Now, maybe the best thing to do is figure out where you are, Waldo, with 4/5 pi. So what I will sometimes do is come over here and draw my unit circle. Okay? I didn't get the axis in too good a place, but we know that's 1/4 pi, 2/4 pi, 3/4 pi, 4/4 pi, 5/4 pi is right down here. 5 pi over 4. That's where you are. Now we got to get our ordered pair. And all the quarter pies, remember, all their xy values are root 2 over 2. So all you have to do now, we know it's a root 2 over 2 and a root 2 over 2. You just have to assign the correct sign. And what's the signs in the third quadrant? Negative, negative. There we have it. So once you have the ordered pair, the rest is a piece of cake, right? Marble cake. Oh, never mind. Okay. So that's sine of 5 pi over 4, cosine of 5 pi over 4, tangent of 5 pi over 4, cotangent of 5 pi. It takes more time to write them out than it does to give the answers, but secant of 5 pi over 4 and cosecant of 5 pi over 4. Okay? What's the sine of any angle? The y value. So that's going to be negative root 2 over 2. And what's the cosine? The x value. And guess what that is? Negative root 2 over 2. And what's the tangent? It's the ratio of these, y over x. Okay? And that's minus over minus is plus. Root 2 over root 2 is 1. 2 over 2 is 1. It's 1. Okay? And what is cotangent? Reciprocal of it? 1. Okay? Boy, I wish I could make it harder, but I can't figure out a way to do it. Okay? Now, what was secant B? 1 over cosine, 1 over x, 1 over cosine, which if you go back and remember that minus root 2 over 2, we got from minus 1 over root 2 when we rationalize the denominator, right? So flip that over and you get minus root 2. Now, you can go back and do it the other way and rationalize the denominator again, but that's the easier way to me. If you remember that's where it came from, that's what it is. And guess what cosecant is? Yeah, negative root 2 also, okay, because those are, the x and y's are the same. And 1 over x and 1 over y would be the same. Now, a couple of things to note here. And I think you'll find this useful to remember too. Remember, I love patterns, okay? All right. In the first quadrant, what can you tell me about all 6 trigonometric functions? They're all positive because x's are positive, y is positive, everything's positive, okay? Over here, we're not there, we're down here. So let's look at this one. What do you notice here? Minus, 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 plus, plus. Up here, I'll tell you this, sine, cosecant are positive, all the rest of them are negative. Here, tangent and cotangent are positive, all the rest of them are negative. Down here, cosine and secant are positive, all the rest of them. Okay? So, all students take calculus or chemistry or whatever you want to do that starts with a C. All your trig functions are positive up here. Only the sine and its reciprocal cosecant. Only the tangent and its reciprocal cotangent. And only the cosine, remember there's several C's here, cosine and its reciprocal secant. Those are what's positive there. The other 4 are negative, negative, negative. Everything's positive. Okay. So that's just another little trick to keep in mind. Okay. All right, to erase everything? Okay. So let's do t is equal to pi. Okay. Again, I'll draw my little circle over here. Try to get my, I still didn't get them in very good places. Where in the world is t equal pi? Where are we, Waldo? Negative x-axis, right there. There's t is equal to pi right there. And what's our coordinates there? Negative 1, 0. So I think we have, well, not now. So we want, whoops, yuck. Okay. We want the sine of pi. We want the cosine of pi. We want the tangent of pi. We want the cotangent of pi. We want the secant of pi. And we want the cosecant of pi. Can you tell me what tangent pi is? I mean sine of pi. Goodness sake. 0. Cosine of pi? Negative 1. Tangent pi? 0. 0 over negative 1 is still 0. How about cotangent of pi? Say again? Negative 1 over 0, what's that value? Undefined. Okay, you can't divide by 0. Whoa, got carried away, didn't I? Secant 0 would be, secant of pi, I'm sorry, which is negative 1, exactly. And cosecant of pi, which is undefined. You got it. Pretty easy, huh? I've been trying to think of a way to make it harder, but so far I've failed miserably, okay? So, I'm just going to erase, let's erase it all. I'll draw my circle again. Okay. Okay. Now let's do t is equal to pi. Oh, yuck. Why is this doing that? Okay. Draw your circle. All right. T is equal to pi thirds. Does anyone, or negative pi thirds? Okay. Now, here's what I think. I think there's a pi, therefore there's a negative pi, right? And a third of that would be about here, and another third about here, right? So, negative 1/3 pi would be right down here. That's where you are. Can you come up with values there? X, Y. I think you're mouthing it right, I think. I can't hear you. Your X value is? I mean, even my ugly picture, you can almost imagine that's exactly 1/2, isn't it? So that's 1/2. And then what goes along with that? Negative root 3 over 2. Once you got that ordered pair, you basically have it knocked, folks. So we want the sine of negative pi thirds, the cosine of negative pi thirds, the tangent of negative pi thirds, the cotangent of negative pi thirds. I probably should be putting these in parentheses, make it look a little nicer. The secant of negative pi thirds, and the cosecant of negative pi thirds. I love when they work on the grass out there. It just makes so much noise. Okay. All right. What's the sign of that? Negative. Negative root 3 over 2. It's just the y value. Okay? There it is. Right there. What's the cosine of that? 1/2. What's the tangent of this? Takes a little more work, but not a whole lot. Notice it's minus divided by plus, so that's going to be minus. The 2's are going to go out. They've been dating, okay? And that just leaves you root 3. Right? Over 1. Okay? So what's the cotangent of that? Negative 1 over root 3. And if you don't like writing it with a radical in the denominator, that would be negative root 3 over 3. You got it. Again, the patterns. How about the secant of negative pi thirds? 2. That's it. Just reciprocal of cosine. And the cosecant of negative pi thirds? Negative 2 over root 3. And if you don't like radicals in the denominator, that would be negative 2 root 3 over 3. Perfect. Perfect. So the first thing, get your ordered pairs. And once you got your ordered pairs, fill in the table. I mean, it's almost just that easy. Okay. So let's erase all this stuff. Y'all all got it? Okay. And let's do, for each t value, begin by finding the corresponding point, xy, on the unit circle, then use those definitions for that. So for t equal pi 6, I should have drawn the unit circle for that. I didn't. What's that? Oh, I think my square was, chair was squeaky. My square was cheeky. Yeah, okay. For this, if you drew the unit circle, that's that first little thing there. Your x value is root 3 over 2, and your y value is 1/2. And frankly, the trig function you just write down from there. The sign would be 1/2. The cosine would be root 3 over 2. The tangent would be, okay, see the 2's cancel out and be 1 over root 3, which is, well, they write it out, 1/2 divided by square root of 3 over 2. The 2's go out, and you have 1 over root 3, and then they carry that one more step to your root 3 over 3. Okay, good deal. Cotangent, oh, they're going to go up and do cosecant, I bet. Why they do that, I don't know. Go up, and that's just reciprocal of sine. I'd write it over there, as you saw where I wrote it. That would be what? 2. Okay? and they do 1 over 1/2 and say that's 2, that's correct. Then they do secant next, which would be 1 over 2 over root 3 over 2, which is 2 over 3, exactly, or 2 over root 3, sorry, I said it backwards, and that would be 2 root 3 over 3, okay? And finally, cotangent, which I would have done right after tangent, would be that, which would be, if the other was 1 over root 3, this is root 3 over 1. Root 3. Good deal. Okay? Wish they'd have it all on the same slide. You could see it better. But they don't. They take up too much room. All right, the B was 5/4 pi. And again, draw your unit circle. Count off how many quarters. You're down in the third quadrant at the quarter pi thing. Those are all root 2's over 2's always. Down in the third quadrant, they're both minus. So we know what sine of 5/4 pi is. What? Negative root 2 over 2. Cosine would be? Negative root 2 over 2, exactly. And the tangent then would be? 1, because they're the same thing over each other. And I wish they'd have done cotangent. What would that be? 1. Remember that. We'll get back to it. They're going to jump up and do cosecant now. And what would that be? Negative root 2, because, oh, well, I'm sorry. I forgot to do tangent. Okay, that's 1. We said it. I didn't write it down. Okay, so cosecant is going to be, negative root 2. Is the reciprocal of negative 1 over root 2, which would be negative root 2. Okay? And cosecant is going to be the reciprocal of cosine, which is going to be the same, negative root 2. They do it all. And then remember what cotangent was? 1. There it is. Okay, good deal. Now let's do, and by the way, these angles here, 0, pi halves pi, and 3/4 pi, 3 halves pi, and all multiples of those are sometimes called the quadrantal angles, because those are the ones on the quadrant lines. They're not in the quadrant, they're at the boundaries. Okay, so sometimes you hear them called quadrantal angles, and those are real easy to pick out the ordered pairs, as you did before. That's negative 1, 0. So the sine is just going to be the y value, which is 0. Cosine is going to be negative 1. The tangent is going to be 0. Took them a while to get there, but they got there. And I would have gone and done the cotangent, would be undefined. They jump up and do the cosecant, which would be undefined as well. Secant would be negative 1, exactly. And the tangent was undefined. Perfect, perfect, because you can't ever divide by 0. Okay? The D one here then, since it's a negative pi thirds, you move clockwise pi thirds, and that puts you down in the fourth quadrant. Fourth quadrant, the x value is positive. That would be your 1/2, and your y value is negative root 3 over 2. Okay? So since you know your x, y, easy to write down the sign. What's that? Negative root 3 over 2. The cosine will be 1/2. The tangent will be negative root 3. You got it. Takes them a while to get there, but there they got it. Now I would be tempted to do the cotangent next. Just reciprocate that, and you have negative 1 over root 3, which is negative root 3 over 3. Remember that. We'll be coming to it. The cosecant, which they're going to do next, is what?
Negative 2 root 3
over 3. Yes, okay. Well, no, okay. It's negative 2 over root 3, which would be, yeah, you said it right, negative 2 root 3 over 3. Okay? And this is negative 2 root 3 over 3. Good deal. Secant. Yeah, that would just be your 2. And your cotangent, we already did that. Negative root 3 over 3. Perfect. Excellent. Seems like a lot, but it's pretty simple to do. They do have some checkpoints at the bottom. Remember those? They're located at larsonprecalculus.com, so but do those as soon as you can. Okay, let's move on to domain and period of sine and cosine. What does domain mean? Oh, boy, what does that mean? All the possible x values. Okay, good. Okay. Now, the domain of the sine and cosine function set of all real numbers because they're defined everywhere. You don't have any place where 0 is ever in the denominator. It's always, the domain is all real numbers. Now, the range, on the other hand, no matter what sine or cosine you're doing, sine and cosine do this. They always stay between plus or minus 1. Okay? So the range is always between minus 1 and plus 1. That's the y values. Never varies from there. X values can go on and on and on. Okay? Because remember, this would be x equals 0, pi quarters, pi half, pi 3/4, pi 2 pi, 4 pi, 8 pi, 6 pi, 10 pi. It goes on forever and ever, x's. And in the negative direction, you can go on forever and ever and ever. But the y's always stay between plus or minus 1. Always. Okay? So by definition, the sine t, that's the range of the sine, is the y values, which stays between plus or minus 1. Cosine of t is the x values. Now, the x values on the unit circle, okay. Let's go back here for a minute. Sorry about this. Domain of sine and cosine are all real function because, remember, it's the sine of t and the cosine of t, not of x. Okay? So don't think in terms of x. Think in terms of t. T can be any real number in the world. Positive, negative, all of them. The range of your sine function are your y's, and the range of the cosine function are your x's. Okay? We usually think of domains as being the x's. Not in this case. The t's are your domain. The x's are the range of cosine, and the y's are the range of sine, because sine is y and cosine is x. So, and the values there are always between plus and minus 1. Okay. So, sine stays between plus or minus 1. Can be plus or minus 1, but not. And cosine stays between plus or minus 1. So, if you're ever answering a question on a test and say, what is the sine, solve this for sine, and you give me 1.3, wrong answer. Sine is always between plus or minus 1. Or negative 4/3. Wrong answer. It's got to be between plus or minus 1. Sine and cosine. Okay. We'll find out the others not, but sine and cosine are always between that. So, this is just going back to coterminal angles, basically. That is, t is pi fourths. It's also pi fourths plus 2 pi, plus 4 pi, plus 6 pi, plus 8 pi. Or, let's just leave it like that. This is pi halves, and pi halves plus 2 pi, pi halves plus 4 pi, pi halves, around, okay. Same thing. So every angle can be represented by itself, or itself plus some even multiple pi, 2n pi. N is any energy, which could be going in the negative direction. Okay. And here pi plus 2 pi would be 3 pi plus 2 pi would be 5 pi. So these would be odd pi's over here, even pi's over here. For a moment. Okay. Not really sure why they threw that in here. I think I know, but okay. So the values of the sine of t plus 2 pi basically is always the same as the value of sine of t, because t plus 2 pi is the same angle, okay? And same, and cosine of t plus 2 pi is going to be the cosine of t. So similar results can be obtained by the repeated revolutions, positive or negative, on the unit circle. So that leads to this general result that the sine of t plus 2n pi, I like to say 2n pi because that gives you the coefficient for the pi. They say 2 pi n. It doesn't matter what order you write. That's always the same sine of t because you don't exactly n times around the circle either way you go. Same with cosine. Okay. Functions that behave in such a repetitive or cyclic manner are called periodic functions. Because after some period, they come back to the same value they were before. Okay? Periodic functions. And remember, way earlier, we called these circular functions. Same type of reason. Okay? Periodic, repetitive, periodic function. Now, what is the period? It's where that amount about which it repeats. That would be every 2 pi. For sine and cosine, by the way. So here's our definition of the periodic functions. The function f is periodic when there exists some positive real number c such that f of t plus c is always the same as f of t. In other words, you go a period of c and you get back to the same value f you had before. Okay? That's for all t in the domain of f. The smallest number c for which that's periodic is called the period. And for sine and cosine, that c is 2 pi. You have to go all the way around to get back to exactly the same place you were before. Now, just a little bit of review from pre-calculus algebra. We say that a function f is even when f of minus t is the same as f of t. In other words, when you go this way and you get some value, if you go this way, you have to get the same value. So that means they reflect across the x-axis. I mean the y-axis, that means they're even. They're odd, however, when f of minus t is the opposite of f of t. So if f of t is up here, f of minus t is down here. They're the opposite. And that means they reflect about the origin. Okay? Now, if you remember, sine is positive here and positive over here too. Okay? So that means the sine starts at 0, positive for the first half and positive for the second half. The one over here is negative. So that makes it an odd function. Whereas cosine is positive, negative, negative, positive. Okay? And that means if you went up here it's positive, if you went down here it's positive. So that means it's an even function. Okay? So therefore, cosine of negative t is the same as cosine of t. It's an even function. So therefore, its reciprocal function, which is secant of negative t, is the same as secant of t. Those are the only two even functions. The other 4 trig functions are all odd. Okay, sine of negative t is the opposite of sine of t, so it's odd. So its reciprocal would be odd. But tangent also, because tangent is sine over cosine, and odd over an even gives you an odd. Kind of like negative numbers. Okay? Not quite the same, but so. So tangent and therefore cotangent are both odd functions. Sine, cosecant, tangent, cosecant, odd, only cosine, secants are even. Not that you use them that much, but when you do need them, that's what they are. Okay. So, I don't like the way they do these problems. They give you the answer and say, see, that's the answer. Okay. What kind of exercise is that? Okay. So, I hate to do this. Forget all that. Okay. What we want to know is what the sine of 13.6 pi is. Okay. Now, first thing I would do to a problem like that, I take a look at it and say, is that within the unit circle somewhere? Well, is 13/6 pi more than or greater than or less than 2 pi? It's greater than, because 12/6 pi would be 2 pi. So this is beyond that. How far beyond it is it? 1/6 pi. So therefore, the sine of 13/6 pi is the same as sine of pi 6. And we know what the sine of pi 6 is, don't we? What? One half. Absolutely, absolutely. Way to go. Okay? The next one is asking you, what is the cosine of negative 7/2 pi? The cosine of negative 7 pi over 2. Okay? Now obviously that's outside one trip around the unit circle, because that would be 4 pi halves. And you're going in the opposite direction. So if you need to, and I should have done it on the other one too, start with your circle, okay? And we're doing half pies, right? There's negative 1/2 pi, 2/2 pi, 3/2 pi, 4/2 pi, 5/2 pi, 6/2 pi, 7/2 pi. You're right there. Where are you, Waldo? What's your coordinates, huh? Yeah, you're the same as pi halves. That's exactly right. That's the same as the cosine of pi halves. And what is the cosine of pi halves? In other words, what's your coordinates here? Say again? 0, 1. And what's the cosine? 0 is the x coordinate. 0. Okay. Now, is it time? Oh, how sad. Ooh, it's past time, isn't it? Guess what? No extra charge today. Okay. I won't. Okay. Okay. We didn't get to do the C part, and y'all are wanting to leave, and you got to go to that thing too if you want to. So we'll pick up with C next time, and we'll go over these two too. Homework exercises here. I know you want these, either 5 or 7 or both. I already assigned those, I think. Maybe not. 9 or 11 or both. Any of the odds 13 through 21. By the way, all those are on calcchat.com. None of them are on CalcView. But starting with 23 through 29, 23 is on CalcView. All the odds are on CalcChat. 31 to 35, 31 is on CalcView. All are on CalcChat. Odds 37 to 41, 37 is on CalcView. All of them are on CalcChat. Okay? We haven't done using the calculator yet, so we'll hold off of that one for now. Okay? So stop at 41. Well, let's see. Doesn't even look like we did for 37, but yeah, I think you can figure it out. Yeah, it's stuff that we've done. Okay. Good deal. Any questions? Okay. Don't forget, if you want to go see the college fair day, that's in the faculty staff